McCarthy.
Did you know that the estimated cost of the 2011 Great East Japan earthquake was $253 billion, making it the most expensive natural disaster in recorded history? Part of that price tag was related to repair and replacement costs of expansion systems in bridges. Now, expansion systems are placed between bridge decks to allow for passage across large gaps that are necessary to account for thermal movements of the bridge. But the vast majority of currently installed expansion systems are not designed to accommodate earthquake movements. They are assumed to fail. By enhancing a common expansion system with shape memory alloy devices, they can be made more resistant to earthquake damage with minimal modifications and low additional costs. Researchers have found these innovative materials to be weather resistant. They have the strength of steel and they can stretch 40 times longer than steel without breaking or weakening. To date, I have tested 6 different shape memory alloy devices and installed them in an analytical joint model that I developed to determine which one best improves the joint's response when it's exposed to a range of earthquake magnitudes. And so I've been able to finalize an optimum design. In the next year, I will provide the bridge industry with a marketable expansion joint that will save federal taxpayer dollars and potentially human lives.
Ladies and gentlemen, Ben Fuselier.
In many places, like California, where earthquakes frequently occur, many reinforced concrete buildings used for things such as schools, apartments, and government buildings have not been designed to resist earthquakes. These reinforced concrete buildings, built prior to the 1970s, and a majority of these still used in commission today, have not been designed based on the codes prior to the 1970s. My research is based on building computer analytical models that represent the typical reinforced concrete building constructed in the prior to the 1970s in the United States. My model newly accounts for the observed damage in the beams, the columns, and the connecting joints between these beams and columns. Using a statistical approach and the observed data with the simulations, we can produce a failure probability for these reinforced concrete buildings. By giving building owners and contractors preventive reasoning to strengthen the critical areas of failure in these buildings, we can help save lives around the world.
Water, water everywhere, but nary a safe drop to drink. In a world of intense use and increasing pollution of our limited fresh water resources, this ancient rhyme may become a modern reality. Let me briefly tell you about several water-related uses and facts relating to the number 9. 90% of the flow of the Trinity River, which is Houston's main source of drinking water, is actually wastewater from the city of Dallas. This wastewater includes many pharmaceutical compounds, such as Tylenol, Oxycontin, and birth control, that pass right through current wastewater treatment systems. Chances are, if you drink a glass of water in Houston, you're drinking somebody else's birth control. 99%. Many of these pharmaceutical compounds can be completely removed from water using a technology I'm researching called photocatalysis. A photocatalyst is a material that takes the incoming energy from light, such as these lights or the sun, and converts it into chemical energy that can be used to oxidize and remove these compounds from the water. I've developed a portable photoreactor system that can be taken to any wastewater treatment plant and used as a proof of concept to test this technology. Furthermore, what we've learned in this research can also help in the developing world, where 900 million people still lack access to safe drinking water. To put that number in perspective, every 90 seconds, the length of these talks on this timer, 5 children die in the developing world from water-related diseases that could be prevented using this technology.
Akwasi Mensah.
If you ain't used it, if you were in Houston in 2008, you would agree with me that the biggest disaster caused by Hurricane Ike wasn't flooding or damage to buildings, but rather it was the citywide power outage it created. It halted water supply, social services, and economic activities, and left many people without power for several days, and in many cases, several weeks. Worst of it all, there was no one who could predict what power was expected to be restored. My research develops a probability-based model to forecast when the scale and locations of power outages, when they do occur, and the expected restoration time. My model also uses probability and recent modern statistical tools, and thus allow users to add information, new information that is gathered just before, during, and after the event, thus allowing increase in accuracy. Most predictive models existing can't do this. The city of Houston is going to implement my model in its online storm calculator and use it to inform decisions making on management, disaster management, and restoration strategies. Welcome the next hurricane season. Consult this model to decide whether you should evacuate or stay put in the event of an hurricane. Thank you.
Imagine we are in a building. Suddenly a strong earthquake or a tornado happens. In this situation, we are at much risk. Any part of the building could collapse. And how would you know which way to get out of the building? Now my research provides a reliable solution to this problem. The key idea is the smart system I developed, which can continuously monitor the structure. Once damage occurs, this smart system can automatically sense the location of the damage and evaluate how serious this damage is. And then it immediately tells the people in the building, okay, here's the best way to go. That way is not because the structure is damaged there. The best part of this smart system I developed is that it keeps going automatically. Another good thing about this smart system I developed is that it can respond to the damage in less than 1 second. Also, it's not expensive. It can be installed in new or old buildings, bridges, pipelines, and other structures. So in a word, this smart system I developed can automatically sense the damage information of the structure so as to protect people even in the disaster events.
Many car companies are working on using hydrogen as the fuel of the future because hydrogen is abundant and clean. The only byproduct of burning it is simply water. However, its storage is a challenge because hydrogen is a gas. Currently, storing it is possible only by applying high pressure, which makes hydrogen fuel systems expensive, if safe at all, especially for hydrogen cars. To address this issue, I have introduced a new 3-dimensional nanoporous material that can serve as a hydrogen storage tank with much higher storage capacity for the same volume. And this comes from its extremely large surface area. In addition, my simulation results show that unlike existing solutions, this material reaches its optimum storage capacity at room temperature and pressure, which makes it even more attractive for mobile applications, such as hydrogen cars. $17 billion global revenue is predicted for hydrogen fuel cars by 2020. Given Rice University's premier international position in developing new nanomaterials, such as buckyball, we're confident that our solution is another step toward bringing clean cars closer to reality.
Fantastic. Fantastic. Civil engineering, guys.